Hello, everyone, and welcome back to your channel of probability and statistics. Today, as I mentioned, we are going to go over how to find the confidence interval or how to conduct a hypothesis testing to find the population of one, oh, I'm sorry, the proportion of one population. So the proportion, as I will show you now, is based on the binomial distribution. Remember, when in the binomial distribution, we say we are going to repeat many Bernoulli trials. Bernoulli trials are trials that have only two possible outcomes. Yes, no, up, down, 0, 1, right, true, false, success, failure. So the binomial, the name bi here meaning you have only two possible values. We call them usually 0 and 1 or success and failure. And we say if I run this experiment n times and I want to see how many times I get a success, then the probability mass function of x given n and p, meaning given the sample size is m or the number of trials is n, and the probability of success is p and it's constant and they are independent, and because they are independent, you can multiply the probabilities. So getting x, if the probability of one success is p, then the probability of x independent successes would be times p x time. But if you get x successes, it must be that you got 1 minus p, which we refer to as q, n minus x independent failures. So q times q times q, n minus x times. So that's basically, and x, of course, can be 0 if you don't get any successes. It cannot be negative. You can get 1, 2, and no more than n, of course, if all of them are successes. We said that mu, which is the mu of x, which is the expected value of x, is np for the binomial, and the variance of x was n times p times 1 minus p. Okay, that's the binomial. I can define now the proportion of successes. So I say, oh, what is the percent of success in this population? Like if I'm doing it for, say, tossing coins, I would expect it to be 50%, like 50% head or tail, depending which one. But I can define P. Again, I don't like the nomenclature here. I prefer to call that pi because that's a population parameter, and we use Greek letters for parameters. But to reduce confusion, because I would say if 99%, if not all the books that I've seen so far, they are using P. I think when I was your age or when I was taking this course, we used pi. Well, my memory is not that sharp anymore, but that's my recollection. However, we'll see P, as I said, to reduce confusion, but keep in mind, even though we are using a letter from the alphabet, a Latin letter, that is a population parameter. And that is x over n. Its definition is x over n, right? So we know that the expected value of P is the expected value of x over n. But since n is a constant, I can take it out times the expected value of x. But the expected value of x is np, so it's np over n. It's just p, which makes sense, right? The expected value of p is p. Okay, but what is the variance of p? Remember, linear combination of random variables. It's the variance of x over n. And every time I told you, you see the variance, you go to the side and say, oh, variance means square, so let me square this guy. That's so easy. It's x squared over n squared. X squared is the variance, so it's the variance of x divided by n squared. But the variance of x is npq, so it's npq over n squared. It's PQ over n. That's it. Very simple. And then we say, but if n is so large, how can I use the binomial distribution? It doesn't make sense, right? If I tell you, oh, what is the probability of getting 70 success or more in an experiment of 150 if p is 0.2? Am I going to add all of these? So we say usually when we have large samples, large binomial, we can let the normal distribution to replace it due to the central limit theorem. However, statistician will tell you make sure that NP and NQ are both greater than or at least 10. At least 10. In the old days, I think we used 5, but now they say to be safe, make it at least 10. Easiest case or simplest case, if you expect P to be 50%, like tossing a coin again, 50-50, then 1/2 N or 1/2 Q has to be greater than 10, so you can use a sample of size 20. But if that was a production line and you want to see the proportion of defective parts, and you expect that the defectives are like, even it's not that good, but at least 1%. This is high, but let's assume it's 1% defective. Then you want to say 1 or 99%, n times 99%, or n times 1% has to be greater than 10. You take the maximum, of course. So so n here has to be at least 1,000 parts that you have to check, right? If it's 100, you multiply both sides by 100, so you get 1,000 as n. Okay. So that's a good thing to check when you are solving a problem. So as we said, we can construct confidence interval. It can be one-sided, meaning a confidence bound, upper bound or lower bound, or two-sided. So for a two-sided, because you can think of the others. So 100 times 1 minus alpha % confidence interval on P. If it's a two-sided, let's say, then you would have P is greater than, less than P0, which you get from the sample, minus Z alpha over 2 times the square root of PQ over N, P0 plus Z alpha over 2 PQ over N. And if it's 100%, 1 minus alpha % upper bound on P, upper bound, meaning it doesn't exceed something, then you would say P has to be less than P0 plus Z alpha square root of PQ over N. And if it's a lower bound, you say P is greater than P0 minus Z alpha. And if you are running a test of hypothesis testing on P, your null hypothesis would always be P equals some value P0. Okay? The alternative hypothesis would be either P doesn't equal P0, or P greater than P0, or P less than P0. Your test statistic is Z, which equals P0, that estimates P minus P, which is the estimate, over the square root of PQ over N. Some people would say, shouldn't that be P0 Q0 over N? Because you are saying, remember when we say X bar minus mu over the square root of over sigma over root N, or over S over root N. And we said with the Z, we use the standard deviation sigma of the population. And then I told you, but we usually, not usually, we invariably we don't know sigma. If we know sigma, how can't we know mu? However, because we are running hypothesis testing, we always start by assuming the null hypothesis is true. And then the burden on finding or proving that it's not good enough, I have evidence to show it's not correct, falls onto the specimen itself. Okay? So now if we assume P equals P0, so we know it, then we are going to if we know P, then we know Q, then we know the standard deviation. Alpha is whatever. You will reject depending on the case. Here you reject if the Z calculated or the absolute value of Z calc is less than Z alpha over 2. Here you reject if Z calc is greater than Z alpha. And here you reject if Z calculated is less than Z alpha. Okay, so let's take an example and see how we are going to do that. In this example, they tell you, remember the problem of the gravel road and the posted speeds? Okay, the traffic authority in this area had the impression or had historical data to suggest that the percentage of people who are exceeding the speed limit was 60%. 60% of the drivers go over the speed limit on a gravel road. And they were worried that this percentage has increased, because if it does, they would, maybe install more radars on this area or something, because it's dangerous to exceed it on a gravel road. So they said, let's collect data. So they went during, some time like where they expect to see many cars, and they found that for a sample of 73 vehicles, X would be the number of cars that exceeded the speed limit, and they found that this number, 60% is 42, 43, so let's say 49 vehicles. Is that enough evidence at 5% to show that P has increased? Of course, if I divide 49 by 73, it's more than 60%. So yeah, of course it did. Oh, no, you have to be careful. We are not talking math. Which one is larger? We know it has to be larger, or else why would I run the experiment, right? If this number is less than 60%, it would be foolish to run the experiment. So all what we want to say is that with 95% confidence, is there evidence that this number, this ratio, is more than 60%? Notice the sample size is not large. So we have a small number here, small sample. But let's do it. So we are going to say zcalc equals 49 over, so P0 here, or if you call that, I keep referring, I think we should say P0 is the 60%. So let's call that's P0, right? According to what we did here. That's what I hate about so that should be pi, really. So let's say P is 49 divided by 73. It's 0.671. So now I have to say 0.671 minus whatever I have in the null hypothesis, and the null hypothesis here, null hypothesis is that P equals 0.6, and the alternative hypothesis is P greater than 0.6. So minus 0.6 over the square root of 0.6 times 1 minus 0.6, which is 0.4, over n. So if I take this percent minus 0.6, and then I divide by the square root of 0.6 times 0.4, which is 0.24 over 73. Oh, reject if the z-calc is greater than 5%. Notice 5% would be 1.645. You can find that from your calculator or tables or a computer. I got 124. Now, here is my normal distribution. Here is the 1.645 that has 5% to its right, but I got only 124. So I failed to reject the null hypothesis. So definitely my p-value is greater than 5%, right? The area to the right of that is more than 5%. How do I find it? Well, the easier way with a calculator is to say, oh, this area is identical to the area to the left of negative 124. So let me use the calculator and find the cumulative of negative 124. And you do that by going to the distribution, select the CDF or the cumulative distribution function. Your lower limit should be negative infinity. So you enter negative 1 EE99, that's negative infinity, comma, and then you pick this number. Oops, I'm sorry. You pick negative this number, right? And that's it, because the mean is 0 and the standard deviation is 1, meaning this is the standard normal, so you don't need to enter any mean or standard deviation. And you get 0.107. The p-value is 0.107, which is greater than 5%. So retain the null hypothesis or fail to reject the null hypothesis. Okay, it's that simple. So whatever is hypothesized here, use it as p times 1 minus that over the n would give you the variance. Take the square root of that, you get the standard error. And then on the top is whatever you found minus whatever was hypothesized. And that's basically it. In the next session, or maybe later, I will do it for the two populations. So I take a sample from each population and check whether the proportion is the same or different, or one is larger or one is smaller. Remember, the alternative hypothesis come in 3 flavors: not equal, greater than, or less than. So it's the same all the way, but you make sure that if it's a two-sided, if that were a two-sided, I would make that 196 and negative 196, and my p-value I would calculate, for example, this portion, and I have to multiply it by 2, because either those areas would be worse or more critical than my sample. And that's the definition of p, the p-value. Okay? Again, as usual, if you have any questions, please leave a note in my comment section, and I will get back to you as soon as I can. Thank you very much and have a great day.